Hello everybody, this is your favorite computer science teacher speaking. This is a revision video all about section 1, which is hardware. So we'll be looking at 1.1, the central processing unit, all the way to 1.7 additional hardware. So it's really important as I'm going through these topics that you've got some paper with you. You could use your remote education workbook, but it's probably a better idea just to have some lined paper. That way you can group all of this information together and use as your revision notes. If you want to make them look nice and pretty, you can use card or colored paper or blank paper, whatever you want to use, as long as you are following along with the video as I'm talking. You might want to pause the video occasionally as I'm explaining something, and I'll get you to draw a few diagrams and other things. The more you get involved with this, the better it will be, because the easier you will remember these different topics. Okay, so we're going to start with 1.1, the CPU. I'd like you to draw this diagram into your book or onto your lined paper. So, an exam question about the CPU will generally ask you to explain the purpose of these three components. So, we're just going to look at the role of each of these, starting with the control unit. So, I'm going to be drawing a few diagrams. It'd be better if you wrote out text rather than diagrams, but you might want to have a mixture. It's always a good idea to have some icons and some images as well to help you remember. So the first role of the control unit is to direct the flow of information and data. So I'm going to draw some epic pictures over here. So it's directing the flow of information and data within the CPU. The second thing that the control unit does is to control the other parts of the CPU. So we've got an epic controller over here. Amazing artwork. So it controls the ALU and it controls the registers. Okay, so the two purposes of the control unit. The next component is the ALU. And the ALU, many people consider as a calculator. You can't write that it's a calculator in the exam because you won't get marks for it. You need to say that its two roles are to perform simple calculations, that's the first role, and to perform logical operations. Those are the two roles of the ALU. So to perform simple calculations and perform logical operations. Okay, the final component is the registers, and I'm just going to draw a box here because it is for temporary storage of data and instructions. So temporary storage of data and instructions during the FDE cycle that we're going to look at in 1.2. Okay, so hopefully your diagram's got some text rather than just some pictures, but you should also have a few icons. The control unit directs the flow of data and information in the CPU and controls the other parts. The ALU performs simple calculations and logical operations, and the registers are temporary storage spaces for data and instructions during the FDE cycle. Okay, also as part of 1.1 we have this diagram, and this diagram represents a certain type of architecture that we use inside of most modern computers, and that is von Neumann architecture. So you don't need to draw this diagram out, but there are three key features of von Neumann architecture that you do need to know. So the first feature of von Neumann architecture is the importance of the CPU. So the CPU has one control unit, one ALU, and one set of registers. Second key feature of von Neumann architecture is memory. So both data and instructions are stored in memory. That allows the computer to multitask. And the third feature of von Neumann architecture is input and output of data into the system and out of the system. There are other types of computer architecture. So Harvard is another type of computer architecture. They have not asked about Harvard in any of the previous exams, but just so you know that there are other architectures do exist, and in Harvard, it is all about the control unit. The control unit in Harvard is the most important part of that architecture. Okay, so for 1.1, you should have make sure you pause the video if you need to anytime. You should have a diagram of a CPU, what the components do in the CPU, and then the three features of volume and architecture. Okay, 1.2 is about the FDE cycle. This is the fetch, decode, execute cycle. In essence, instructions are fetched from RAM and brought into the CPU where they're decoded, which means to work out what they need to do, and then executed, which means that they are run. There are three registers that are very important in the FDE cycle. So you might want to draw these icons out. First register is the program counter. And the program counter's definition is that it keeps track of the memory address of which instruction is to be fetched next. So for example, let's simplify and imagine that RAM is made up of 200 squares. So 200 addresses in RAM where all of my instructions can be kept. And my program counter might tell me to look at address 56, for example. Okay, so the program counter is pointing to a specific address in RAM of where your instruction is that you need to fetch next. The next register that we need to know is the memory address register. So the definition of this register is that it stores the address in RAM that is currently being read or written to. So the address in RAM that we are currently using. So what happens is, the program counter tells us where to look. We then take that value, take that address, 56, and we put it into the memory address register. Just want you to think about why we take 56 and we move it and put 56 in another register. What's the point of that? The reason we do that is because the program counter needs to be increased for the next cycle. So while we are moving on to the next stage of the FDE cycle, and we're about to fetch from RAM, the program counter can move up and get ready for the next one. So all of these things are happening extremely quickly inside of the CPU, and you can't waste any time. So we use a separate register to tell us exactly where this instruction is going to be fetched from. Okay? So I'm explaining both the registers and how the FDE cycle works at the same time. So now that the computer knows to look in 56, it will go to RAM, it will go to address 56, and it will fetch that instruction. So that is the fetch stage complete. So the fetch stage is checking the program counter to see where the address is, moving that address into the memory address register, and then going to that address and fetching that instruction. That instruction is fetched and brought into the CPU, and it is put into a current instruction register. Okay, so the definition of a current instruction register is the storage space for the instruction that has just been fetched from memory. So the storage space for the instruction that has just been fetched from memory. Okay, now it is on to the decode part of the FDE cycle. So you might want to pause the video as I've been explaining the fetch part and now the decode part, because we've looked at the three registers now. So I'll just recap everything actually right now really quickly. So the fetch, you check the program counter, step 1. You move the value into the memory address register. You increase the program counter by 1, ready for the next term. You then look at that address in RAM and you fetch your instruction and you bring it into the current instruction register. Now what we can do is decode that instruction. So imagine the instruction is 8 plus 3. So really simple calculation. So 8 plus 3, the computer now, the control unit, will decode and it will work out what needs to be done. So it knows that it is a maths problem, so it's going to execute it using the most appropriate component. And for a maths problem, the most appropriate component is the ALU. So it will send that instruction to the ALU to be worked out. And the instruction has been executed. Now it can go back, it can go to 57, and then after that 58, 59. And it's doing this billions of times a second. So the FDE cycle can be a little confusing, but really the answer is there for you. Fetch the instruction from RAM, and you know to do that because the program counter tells you exactly where to go. Bring it into the current instruction register to decode it and work out what needs to be done, and then execute it using the most appropriate component, such as the ALU for a mathematical problem. Okay, you might want to pause the video again. You can pause it at any time. Obviously, you don't have to do this entire setting in one go. You might want to, I don't know, look outside, look at the sun. It's October in the UK, so it's probably not sunny, so just close the curtains and let's get back onto 1.3. So 1.3 is all about primary storage. There's 4 types of primary storage that we need to know about. And primary storage is more commonly known as memory. So the M for RAM and ROM stands for memory. We're going to look at each of these in turn. We'll start with RAM. So RAM stands for Random Access Memory. And the data that is stored inside of RAM are all currently running programs. Okay, so you're using a web browser to watch this video, so that is currently being stored in your computer. You might have other tabs open, other applications. They are all currently being stored in random access memory. The operating system going on in the background is also stored in random access memory. So the 2 things that are stored are all your currently running programs and the operating system running in the background. For each type of primary storage, you can also classify them as volatile or non-volatile. So if something is if something is volatile, it means that when you turn the power off, the data is deleted. So RAM, for example, is volatile. So if you are watching a video and you just turn the power off straight away, when you turn your computer back on, that video is still not going to be playing because it's been deleted from RAM. As opposed to non-volatile. So you turn your computer off for non-volatile storage, the next time you turn it on, the data is still going to be there. So it's long-term storage of data. So let's look at ROM next. So ROM stands for read-only memory. And inside ROM, we store the boot up or start up instructions, sometimes called bootstrap instead, or load up. There's all sorts of different words for it, but for this, I'm going to call it the boot up instructions. And it's very important that your boot up instructions are there waiting for you when you turn your computer on. Otherwise, your computer is not going to start. So it's very, very important that this is non-volatile. Okay, so you could do this as a spider diagram, you could do this as a table, however you want to do it. The important information is what is stored in it, and is it volatile or non-volatile. Okay, next we have cache memory. So cache memory stores your frequently accessed data because it is so quick. Cache memory is very, very quick because it is right next to the CPU. So you store your frequently accessed data there that you want to access repeatedly. And it is volatile, just like RAM. Okay. The final type of memory, they haven't actually asked about in any of the previous specifications, because flash is just another word for solid state. So we're going to look at solid state right now, actually, in 1.4 secondary storage. But if they do ask about flash, it is used for storing long-term files, so documents, pictures, videos, and it is non-volatile. Think about a USB stick. USB stick is taken out of a computer, but all the data is still on there. It's saved. And when you plug it in again, you give it power, all the data can be accessed again. Okay, so these are the four types of primary storage. Next, we have secondary storage. So before I talk about these types of secondary storage, there are 5 characteristics that you need to know. So make sure you've got a list of these. So whenever you're talking about secondary storage, you need to think about these 5 characteristics. And they are capacity, so how much data can be stored. Durability, so how long can that device last without breaking, without snapping. Portability, so can you carry that device around easily in a bag or in a pocket. Access speed, so how fast is it to access the data that you need. And cost, how expensive is that device. So starting with magnetic, actually let's copy this. Starting with magnetic, we're going to look at each of these in terms of these 5 characteristics. So magnetic includes the hard disk drive, HDD, the magnetic tape, and then older formats as well, such as floppy disk or even VHS, like the old videos. So magnetic is a type of device that has a high capacity. So we're just going to tick it. It'd be better in your book or on your paper if you don't just tick like I'm doing. I'm just explaining it very quickly. So it's got a high capacity. It is in a metal case, so usually it's quite durable. Just make sure that you are not carrying it. If you're not picking up a computer like a desktop while it is in use. Because it might damage the platter, might damage the read-write platter. Portability is generally quite good. So an external hard disk drive, for example, can be quite portable. If it's the hard drive inside of your computer, then obviously you can't take that out and replace it. But generally, if it's a hard disk drive, an external version is quite good. Magnetic storage access speed is good, but it is not as good as solid state. So it's not as fast as solid state. And then cost is good. It is cheaper per gigabyte than solid state. So a 2 terabyte external hard drive might cost you about £60. A 2 terabyte solid state drive might cost you about £200. So it can be 4 times more expensive. Okay, optical. The capacity in optical is very poor. It's less than a gigabyte for a CD. That's why CDs only have about 14 songs on them maximum. So if you ever bought a CD compilation and it comes with 4 different discs, that's because it can't store all the songs on one disc. Durability is also not very good. Discs can easily be scratched and damaged. Portability, very good. Disc is very thin, so it can easily fit into a CD case and be carried around. Access speed is poor. The disk has to spin to where the next data is. So if you're listening to a music CD and you're going from track 1 to track 7, you might realize that you have to wait even a second or two to get between the points of data. But cost, it is very, very cheap to buy a disk. So optical includes CD, DVD, and Blu-ray. Okay, solid state. Capacity, very high. Durability, some cheaper USB sticks can be snapped, but generally they have a good durability, especially external SSDs. Portability, very good. You can fit a USB stick in a pocket. Access speed. So out of all of them, solid state is the fastest to access. But the only downfall for solid state is the cost. Like I said, it can be 4 times as expensive as magnetic storage. And lastly, cloud. Cloud is an interesting one. They're generally not going to ask you about these 5 characteristics in an exam because cloud all depends on your network. So if you're running on a fast network, access speed is going to be great. If you're running on a slow network, access speed and then everything else is going to be very poor. So cloud storage uses the internet to store your data. So it uses servers provided by Google if you're using Google Drive, Microsoft if you're using OneDrive, iCloud is from Apple. So your data is in their hands. If something happened to their data servers, then you wouldn't be able to access your data. So really, it's question marks because it all depends on your network. Okay, the next topic is performance. Just before we move on to performance though, I've just forgotten to add here data sizes. So data storage units falls into 1.4, and this is just the relationship between the different sizes of data. So we start with a bit, which is just a 0 or 1. So it'd be a good idea to have a list of this as well. Start with a bit, which is 0, 1. Then 4 bits is called a nibble. 8 bits is a byte. 1024 bytes is a kilobyte. So a kilobyte might be a couple of paragraphs of text. 1024 kilobytes is a megabyte. So a megabyte might be a short snippet of a song. A gigabyte is 1024 megabytes. So you can see USB sticks with 4, 8, 16, 32, 64 gigabytes. A short movie might be a gigabyte. Then you've got a terabyte, which is 1024 gigabytes. And terabyte is usually the hard drive standard these days. So a magnetic hard disk drive might be a terabyte inside of a laptop or a computer. Then you've got a petabyte. Ooh. Now that's 1024 terabytes, and we're starting to get into the stage where it's a lot of data, so it's difficult to quantify. Then we've got an exabyte, a zettabyte, and a yottabyte. So a lot of data. We only need to know really up to petabyte. They've never actually asked above that before, but if you forget, it is easy to remember. EZY, easy to remember what goes above petabyte. Okay, remember to take a break and to pause as we're going through this, because this shouldn't all be watched in one go. Now we've got performance. So these are 3 factors that affect how quickly the computer can run applications and perform tasks. So the first one is cache memory. So the more cache memory that you have, the faster your computer is going to run because it is closer to the CPU and can therefore access data much more quickly. So the more cache memory you have, the faster your computer will generally be because it's much closer than other types of memory such as RAM. For clock speed, you can, that's actually not used green, you can overclock your computer, which means to increase the clock speed. So say your computer's default clock speed is 3.5. If you overclock the computer, you can raise that to 3.7. So your computer can perform more and perform the FDE cycle quicker per second, but that didn't really work. That's meant to be, I don't know what this is meant to be. I don't know what that's meant to be. It's meant to be like a skull or something, but that is just, wow, it's just making it worse. Let's just stop. Okay, so it wasn't meant to write there, was that it decreases the lifespan. So let's just put an X and let's forget that ever happened. For the clock speed, you can also underclock. So that means you lower the speed of a computer. So if you have a default of 3.5, you can lower it to 3.3. So obviously your performance is going to decrease, but in the long term, the lifespan of the computer is going to be preserved. And finally, we have the number of cores. So one core is a single core computer where you have one control unit, one ALU, and then one set of registers. A dual core computer is where you have two. And a quad core computer is 4, and a octa-core computer is 8. So the more cores that your computer has, the faster that instructions will be able to be processed, because you can process more than one instruction at the same time. So if you've got one core computer and you compare that to a dual core computer, the dual core computer could in theory be twice as quick. 4 core could be 4 times as quick, octa-core could be 8 times as quick, because you can process more instructions per cycle. However, that's not always the case, because you might be waiting on another core. So if you've got a 4-core computer, core 3 might be waiting for core 1, and core 1 might be waiting for core 4. So it might not actually be 4 times as quick, because the different cores are waiting for each other. Okay, so that's performance. Cache memory, clock speed, and number of cores affect the performance of your computer system. 1.6, we're going to start out with buses. So here's an amazing picture of a road that I drew. When you think of a bus, you think of a bus going along the road. So some people think of the bus as that's where the data is. So the data is put onto the bus and the bus moves across the road. But it's not like that at all. The bus is actually the road itself. So the road is the pathway along which data can be sent. Okay? So the bus is the pathway along which data is sent across the motherboard and across the computer. And there are 3 types of buses that we need to know about. We've got the address bus, which sends the address in RAM of where data is stored. So that's obviously using the FDE cycle. We've got the data bus, which sends data from one component to another. And lastly, we've got the control bus. And the control bus is used by the control unit to send control signals to other components. So we talked about how the control unit controls the other parts of the system and of the CPU. So the control unit can send those control signals to other components. Okay, so these are the 3 different pathways that we have inside of a computer: address, data, and control, all sending different values. Okay. If you haven't taken a break already, please take a break. I cannot wait for this to be completed, so we can move on, obviously, to section 3, 4, and 2, 5, 6, and 7 in our other videos, because we've got a lot to get through. But if you're watching these videos, you're taking your time, and you're not trying to do it all madly the night before. So hopefully, you're not watching this video in November, the night before the exam. You're watching it in October when it's been set. Okay, so instruction sets. An instruction set is a list of the instructions that a CPU can process in the FDE cycle. And they're split into 2 types: RISC, which is reduced instruction set computer, and CISC, which is complex instruction set computer. So just going to compare these 2 types of instruction sets. So a RISC has fewer, so I'm going to put here hashtag meaning number. It has fewer instructions that can be processed as part of the FDE cycle compared to CISC, which has more instructions. Therefore, there's the clock. Therefore, RISC is slower for carrying out complex tasks because it has less instructions, which means you might need to use more instructions for a task that CISC can use. So CISC is quicker for complex tasks. RISC uses less power because they are quite basic, so they use less power compared to the more complicated type of instruction sets. RISC runs at lower clock speeds. So I'm just going to write in there. I can't think of something to represent clock speed right now because I've just used the clock. So it runs at lower clock speeds. That's important because some of your simpler devices will use RISC because it's just not powerful enough to handle the complex instruction sets. Okay, so RISC has fewer instructions, takes longer to perform a task, but it uses less energy and can run at lower clock speeds. CISC has more instructions, means it's quicker to complete a task. It uses more power, however, and it needs to run at higher clock speeds. So those are the differences between your two types of instruction set. Okay, on to the final topic now, and we've got hardware. So the motherboard, the graphics card, and the sound card. So the purpose of a motherboard is to connect everything together. So I'm just going to connect it. Nice and easy. Okay, so connect the different components of a computer system together, such as the CPU, ROM, and any expansion cards. So it allows data to be sent from one location on the motherboard to another. The graphics card produces graphical images so they can be displayed on a monitor. Okay, so the graphics card, the GPU, is actually a processor. So the P stands for processor, the U is unit, and the G is graphical. So it's graphical processing unit to display those graphics on a monitor. So there's a lot of processing going on. So it's for processing of video data, of graphical data to be displayed on a monitor. And another type of expansion card is a sound card. So the sound card converts your analog waves. So if I'm singing into a microphone, as I never do, it will convert that into digital data, binary. Remember that computers can only understand and use binary numbers. So the sound card needs to convert your music into a format which is going to be understood by the computer. And likewise, if you're watching a YouTube video and you want to hear the music, it needs to convert that binary data on the web page and turn it back into an analog sound so that we can hear it and we can listen. One more difference between expansion cards is that you can get a dedicated sound card and an integrated sound card. So an integrated sound card is part of the motherboard. So it uses the computer's memory. It's not as powerful, and it just won't give you as good a quality of graphics or sound. The other type is a dedicated expansion card, such as these two here. So a dedicated graphics card and a dedicated sound card. And they're connected in the PCI slots to the motherboard. They have their own memory so that they can not use the computer's memory. And they are much faster, but they generally have to also produce more heat. So the reason a graphics card has a fan is because it's generating a lot of heat because of the extra processing that it is doing. These can also be a lot more expensive than an integrated card. Okay, and finally, we've got our embedded system. So an embedded system is a computer chip. So it's basically a CPU, which this is the worst picture of a CPU I've ever drawn. Don't really know what's going on. So it's a CPU inside of a larger machine. So for example, a really good example is a control chip inside of a washing machine. That way, you can just press a few buttons and you can control exactly the different cycles that the wash is going to be on. Other examples include traffic light systems. You can get them on other devices as well, like a microwave. So it is a control chip. It's a computer system that performs a specific task that is built into a larger device. They use a combination of hardware and software to control that device. And a common example is a washing machine or a traffic light. Okay, so this sums up all of Section 1 hardware, 1.1 to 1.7, everything that you need to know for this first topic. The next video is going to look at network, Section 3, because Section 2 I will mix in with the final topics 5, 6, 7. If you've got any questions about anything that I've been through in the video, just post a comment to this assignment post and I'll be able to see it and I'll be able to respond to it. Have a glorious day and make sure you keep clicking on CS Noobs because I need those views. Joking. Okay, goodbye everybody.